lecture of Unit 2. Microscopy is the use of light or electrons to magnify objects. The units of measure in most light microscopy will be in micrometers or microns, which is 1/1,000,000th of a meter. In electron microscopy, the nanometer is more common, which is 1/1,000,000th of a meter. The wavelength is the distance between two corresponding parts of a wave. Visible light is the wavelengths between 400 nanometers at the violet end to 650 nanometers at the red end. White light is at approximately 550 nanometers. Magnification is the apparent size of an object. It is indicated by a number and an X. It is the result of the refraction created by the curve of the lens or magnetic field in an electron microscope. The resolution is the ability to distinguish between two objects close together or see them as two separate objects. The modern microscope has a resolution of about 0.2 microns, depending on the wavelength of the light or electrons and numerical aperture. The numerical aperture is the ability of a lens to gather light. The resolution formula can be used to calculate the resolution. The resolution distance equals 0.61 times the wavelength divided by the numerical aperture. Contrast is the difference in intensity between two objects. Contrast will improve resolution, so most microbes are stained for that reason. Bright field is the most commonly used light microscopy. With bright field, the background or field is illuminated. A simple microscope uses a signal magnifying lens, similar to what we consider a magnifying glass today. This was what was used by Leeuwenhoek in 1673. Compound microscopes use a series of lenses for magnification. This type of lens was in use as early as 1590 by Galileo, but it was not until 1830 that the clarity of a compound lens could exceed the clarity of a simple lens. Compound microscopes are widely used today. The objective lens is found immediately above the object being magnified. The ocular lens is found closest to the eye and typically magnifies to 10x. The total magnification is determined by multiplying the magnification of the object times the magnification of the ocular lens. The condenser sits below the stage and directs the light through the specimen. Older micrographs used mirrors and prisms to direct the light to the camera to take photos of objects underneath the microscope. Today, the majority of the pictures use digital processes to capture the images. In dark field microscopy, the specimen is made to appear light on a dark background. The dark field stop prevents light from entering the condenser. Here is a short video on using a microscope. There are several different models of microscopes out there, but the technique is very similar for any microscope.
Hi, I'm Professor Oscar, and I'm going to show you how to use the microscope and name the parts. Up here we have the eyepieces or the oculars, and then down here we have the objective lenses, and this is a revolving nose piece that allows us to turn and change objectives. The objectives usually are in 3 magnifications, and it says it right here, 4. The medium-sized one is 10, and the big one is 40. and they click into place. When the objective is in the right position, it's kind of locked into place, so you want to make sure that occurs.
The microscopes we will be using in class will also have a 100x magnification that we will use with oil.
Alright, then there's a hole in the stage through which the light can pass. This is called the stage. This is called the mechanical stage, the part that moves the slide back and forth. Beneath the stage is a condenser which focuses the light, and also what's called an iris diaphragm. If you look here, this little lever here can adjust the light. In addition, there's another adjustment of the light over here. Is a dial that goes from 10 down to 1. And 1 is low and 10 is high. In addition, there's a switch in the back that turns the light on and off. If you're not using the microscope, you should, actually some are in the back, this one happens to be in the front. If you're not using the microscope, shut it off. Okay? So we're going to be looking at it. Focus. So you use these focusing knobs. For the 4-power objective, use the large knob, which is called the coarse focus knob. And then when you use the other lenses, use the fine focus knob. Alright, so I already have the slide here, but let's say we were putting in a new slide. So you take the slide and you put on the stage, you move this little arm over like so, and then you put the slide on. So I'm going to do that. And then the slide nestles into this space between the arm and this sort of bar over here. Slide is nicely in position, and you could move it this back and forth and sideways as well. Then you're ready to look through the microscope, and then you would take your, if you have glasses, as most people don't, you would take your glasses off, otherwise you just look through, and then you may see something, you may not. And then if you don't, you should try focusing to make the image sharp. Also, maybe what you want to look at is not in the field of view, is not underneath the lens. So you may want to move the slide around to look for other parts of that look interesting. And your teacher would be a guide to you as to what looks, and your lab manual as to what looks interesting. All right, let's say you want to go to higher power, from 4 to 10 on the objective. You first have to have it in focus under 4, and then you could switch to 10. And at that point, you still have to focus, but only using the fine focus knob. Don't use the coarse focus anymore, only the fine focus knob. And the same thing would be repeated if you have it in focus under 10. Then if you want to go to 40, you turn the 40. Notice the 40 power is right near the slide, and then definitely you only use the fine focus knob, the small knob, and you only turn it a little bit, one way or the other way, until it's in focus. Do not turn it and turn it, otherwise You can break the lens and also break the slide. All right, well, let's see if there's anything else we've left out. I don't think so. That just about covers our little story on the microscope. Thank you. Press the button.
So again, you will have access to these links outside of this presentation. Hopefully that video will play smoother for you on your own computer than it is on the one I am making this presentation on. Phase microscopes can be used to view microbes as well. The phase contrast microscope can view living organisms that would be damaged by affixing them to slides or staining. This uses two sets of light rays which will appear bright when the waves are in phase and dim when they are out of phase. The differential interference contrast microscope, or Nomarski microscope, creates interference patterns. When the light is split into its components, there is increased contrast and shows a 3D image. Fluorescent microscopy uses UV light source to fluoresce objects. It has a shorter wavelength and increased contrast because of the dark background. Fluorescent dyes must be used. This technique can be used to view some organisms like Pseudomonas aeruginosa and Bacillus anthracis. The confocal microscope uses fluorescent dyes or antibodies and UV lasers to illuminate objects in a single plane no thicker than 1.0 microns. The slices produced are digitized onto a computer to create 3D images similar to an MRI. Electron microscopy uses wavelengths that range from 0.01 nanometers to 0.001 nanometers versus the light microscope using 400 to 650 nanometers. They can magnify images from 10,000 times to 100,000 times. With the TEM, or transmission electron microscopy, a beam of electrons is generated for the image on the screen. The object image is enhanced with electron-dense stains. Specimens must be specially prepared to be viewed by an electron microscope. They must be in a vacuum and sliced very thin, dehydrated, and put in plastic so the specimens are only 100 nanometers thick. SEM, or scanning electron microscopy, uses electrons to view the specimen surface. Objects are magnified up to 10,000 times with a 20 nanometer resolution. Again, the specimen must be in a vacuum, but the whole entire specimen can be observed.
The electron microscope consists of a cylindrical tube about 2 meters long, which is completely devoid of air. In contrast to the light microscope, the electron microscope visualizes objects using a thin beam of rapidly moving electrons that interfere with the specimen placed in the tube. The electrons are emitted by the cathode at the top of the tube and then accelerated by the anode. They then pass through a small aperture, which forms them into a beam, and into the vacuum inside the tube. The part of the microscope that generates the electron beam is sometimes called the Electron Gun. The beam is maintained along the tube by means of electromagnetic lenses. These are coils that surround the tube at given intervals. The electromagnetic field emitted by the coils focuses the beam at the center of the tube. Electrons encounter the specimen and are either absorbed, scattered, or pass through it. Because different regions of the specimen are variously transparent to electrons, different amounts of electrons, with changed energy, pass through these regions. At the end of the tube, the electrons are collected on fluorescent or photographic film, or on screens that generate an image of the specimen. The beam that reaches the film consists of the different amounts of electrons that pass through particular regions of the specimen. This difference is responsible for the contrast in the film. The original image produced by the electron microscope is always black and white, and it is not possible to see it directly with the eye.
Probe microscopy is relatively new. This method uses pointed electronic probes to magnify up to 100 million times. The STM, or scanning tunneling microscope, uses a flow of current between the probe and the specimen to view the surface. The specimen must be electrically conductive and can be measured as small as 0.01 nanometers. The AFM, or atomic force microscope, measures objects using deflection of specimens that do not conduct electricity, can be living, and a vacuum is not needed.
For the observation of particles no bigger than a few billionths of a meter, researchers invented a new microscope, only to discover that it could manipulate atoms too. With this tool, seeing is touching. Like a blind man's probing stick, the tip of the microscope feels the atoms to display their